stage is yours.
Thank you. Yeah, thanks. I feel like most of you know me. For those who don't, I'm a professor at Princeton Chemistry in the chemistry department, and we are interested in two main aspects in my group, which is one is finding chemical rules to predict new topological materials, and the other one is exploring new two-dimensional materials. Because I have only 25 minutes here, I focus on the on the topological aspect. However, I kind of want to talk about the two-dimensional, as you can see, so feel free to chat with me after. Just in general, we are interested in between the interface of chemistry and physics, which is why we have this group logo of a brain that thinks about both of the disciplines, because I think whenever you marry two fields, you can have the opportunity to come up with something new. And therefore, it's always worth to think about interfaces of sciences. I'd like to highlight this article about chemical principles and topological semimetals that I wrote, which is just a chemistry view about the field of topology in general, but also topological semimetals. And so I'm going to tell you my line of thinking a little bit on this talk. I'm going to do it a bit shorter because many of you saw the talk already. So please feel free to talk to me after if this is the first time you hear about it. Just in general, to bring each other on the same page, is that in chemistry we think a little bit different about electronic structures. So you would all tell me an electronic structure is an energy versus momentum diagram, and you can calculate energy by putting up some Hamiltonian. But if I go teach this in my advanced inorganic chemistry class, usually I realize the students don't really want to look at Hamiltonians, but rather draw pictures of orbitals. And so we have a kind of different approach of drawing band structures, which is related to this model pointed out by Roald Hoffmann in this article down here, which I really highly recommend. It's a beautiful written article. And so basically, this is a model of a 1D chain of hydrogen atoms. When white goes, a pious distortion. Basically, you can follow the same models by just drawing orbitals in different colors and they have different phases. So if you would put this atomic orbital here, a plus sign it's white, and then a minus sign it's black, and then you just look that all the ones with the same color can overlap, and if it's maximally bonding because they can overlap, you have a low energy and you get a higher energy if they don't. And then depending on how you define your unit cell, you have either the 4 brillion zone or you have to fold the band structure. And once you fold it and you shorten bond length, you will also see from the distances here that you will have a gap opening. Okay, so this is a simple way of just drawing spheres in different colors and getting the idea of a band structure model. And so why am I so interested in this? Because this is a very simple and intuitive way of understanding graphene from a chemical perspective. Because as a chemist, we would look at graphene as just a carbon atom with 3 chemical bonds that are localized or sp2, so we don't really need to think about them, and then one single pz orbital which has 1 spin. So the way actually we teach band structures first to chemists is to just draw this like blobs of bands, and they would draw a filled pz orbital and a half-filled pz band. It's also a band like that, but then you could technically extend it into a momentum versus plot, and you would just draw a half-filled p band. Okay, but for this reasons, a chemical intuition tells you why graphene is a metal, but not necessarily why it is a topological semimetal. You will only see that if you look at the crystal structure, and you all know this very well, that we have 2 different atoms in graphene, or 2 chemically equivalent atoms actually, but 2 in the unit cell. And because they're 2 chemically equivalent atoms, we learned from Roald Hoffmann that this requires folding of a band structure. And if we now start folding it and extend it to another brillion zone, you get a really, really rough sketch of a Dirac cone. I mean, of course, this is not the accurate band structure of graphene, but it captures the features we have. Okay, so we can just learn that simply from a chemical perspective, having 2 chemically equivalent atoms in the unit cell does something to our band structure, which makes it potentially interesting towards topology. And so the one thing which is different from this and the hydrogen atoms is that we have this band structure now, and in a 1D chain of hydrogen, we said there will be a distortion, a pious distortion that opens it up. In graphene, there's no such distortion, and there's actually a good chemical reason for that, which is that the pz orbitals are delocalized over the full sheet in graphene, and this is called a conjugated or delocalized pi bond in chemistry. And if you were to do anything with this differently, like we would localize it at double bonds, or we would put boron and nitrogen at different electronegativities here, or we would form a fourth bond, we would always gap out this cone in a trivial way. Right? So we can conclude from this that having two things are chemically important: having a delocalized chemical bond and having two chemically equivalent atoms in the unit cell. So with this, we can start to try to get some chemical principles for finding topological materials. First, I wanted to think about different types of bonds I know in materials and how can I relate these bonds to delocalized bonds. So there are ionic bonds, obviously, like you know them in rock salt, and whenever I have just strongly ionic bonds in the solids, most commonly these materials are just permeable insulators. There's, of course, a few exceptions, but commonly. And the same is true for strongly covalent bonds, like we know them in silicon or diamond. So these are called 2E2C, which means 2 electron, 2 center bonds. It means just that a chemical bond is formed between two atoms by 2 electrons. And if I just have these, then I also usually have a trivial material. And then I have these delocalized bonds, as in graphene or benzene, and I can apparently get direct crossings. I mean, of course, I don't get them in benzene because I just have a molecule. I need them to be in a few more dimensions. And so that started me wondering, it's like, okay, there are these features, and I'll show you a few in a second, where you have things that are called 2 electron 3 center bonds, or 2 electron 4 center bonds. And I was wondering if this is the first chemical way to get towards the delocalized bonds. And so, for example, there are these hypo or hypervalent bonds known in molecules. For example, if you have BH3, so here's a very simple chemistry rule. You always have to count to 8 to know if a molecule is happy. So each atom wants to have 8 electrons. But in BH3, boron has only 6 electrons. So it is electron deficient. And because of this, 2 of these BH3s form dimers, where they bridge over 1 hydrogen atoms, and 2 electrons bridge these 3 atoms here in this dimerized molecule. So here I have kind of some delocalization over a shorter range. And so I was wondering if these kind of chemical bonds can be used in a solid, or find in an extended solid and then have the same results as in graphene. So you can also have the opposites, that you're not electron deficient but electron rich. These are the hypervalent bonds. An example is phosphorus pentafluoride, where you would have 10 electrons because each of these bonds donates 2, and the phosphorus is too much, it's more than 8. So if you extend this, if you look at the real bonding in this molecule, you will have a 4 electron 3 center bond right here over the phosphorus, where your electrons are delocalized over this range of the molecule. So we get some local delocalization in the molecules, and these kind of electron delocalizations are actually pretty common. So can we have them also in solid and extended in 1 or 3 dimension, was what I was wondering. And so I found a paper again by Roald Hoffmann, who described these antimony chains, linear antimony chains with 7 electrons, or a square nets of antimons with 6 electrons. And he says they violate something which is called the Zindel concept, which is an electron counting rule in solid-state chemistry, which basically counts to 8. So they violate this one, so you cannot count to 8 in these ones, so they have to be hypervalent. Let us look at why they are hypervalent. So antimony has 5 electrons in the element. So if you have an antimony minus network, each antimony has 6 electrons. And so if you look at this, if each antimon has 6 electrons, it would want to form 2 bonds to get to 8 in total, right? There's 4 electrons are fine and happy, and 2 single ones that want to form a bond to come to 8. But it doesn't only form 2 bonds, it forms 4 bonds. It means it has 6 plus the electrons of each one, so it's too many, so it must be hypervalent. So it must use multicenter bonds delocalized over the whole sheet in order to get this into a chemical reasonable bonding sense. And so this model actually then solved the reason for me about a compound I studied some time ago is zirconium silicon sulfide, which has Dirac cones in a band structure, but also has these square nets of silicon. In this case, not antimony, but they have this exact same electron count. So you also have the square net, and you have 6 electrons per silicon. So you have the same kind of hypervalent bonding mechanism in these compounds. And so just if you want to look at the band structure again, you also have these really, really steep Dirac bands, similar to graphene, but crossing the beryllium zone more often because you have nodal lines. And this has been verified by Arcus Mod. Okay, so chemical delocalization and Dirac cones, at least here's an example that we might be onto something. I just wanted to understand why in a square net arrangement I can have these band crossings also, and not just in a honeycomb. And so this is the Horowitz-Hoffman approach at looking at the orbitals and how they overlap and drawing a band structure. It's the same result you get for a simplified binding model, but Raquel made for me, so I have a figure to show. But if you just look at the square net, a normal square net, you won't see any steep band crossing. So this alone, like the hypervalent bond alone, doesn't explain that to us. Okay? If you look at the crystal structure from zirconium silicon sulfide more carefully, you will see that the silicon square net is actually centered. So therefore we have two atoms of our unit cell again. So we again have two chemically equivalent atoms in the unit cell, which was our second tool we need to have. And because of this, we have to fold the band structure. And once we fold it, we get the linear crossings also in the tight binding model. Okay? So again, so we need the two rules, because two chemically equivalent atoms by itself won't do it, because the Fermi level can just be anywhere in the band structure. But if we combine this with a chemical delocalized bond that is present in the molecule, the Fermi level will be automatically at the crossing point in this band structures. Okay? So two simple chemical rules. So, oh yeah, here's the, here we could be here if we have just a different chemical filling, a no delocalized bond, just a normal ionic bond, our Fermi level would be up here, wouldn't matter, but because of a delocalized bond, we're here. So we were interested in if we were able to quantify this for all the compounds that we know that have these square net arrangement of atoms and structures. So first we look at just one structure type, which is isoelectronic to zirconium silicon sulfide. And so there are lots of materials, more than 500 of these known, and this is just periodic tables of which elements can be at which position. Basically our hypothesis was, if the chemical delocalized bond is what is driving this whole band structure, or is one part of driving the band structure to be real, we want to have a shorter bond distance between the atoms in the net than to the next layer above or below of this thing, because then we can say they're bonded to each other in a chemical way within the square net, otherwise bonds would probably also form in the other direction. Okay? So we just went and looked at all the CIF files and plotted these bond distances, and we made this more rather complex map, but this distance factor is plotted right here on the y-axis, and whenever we are below 1, we fulfill the rule of having a chemical delocalized bond, and when we are above 1, we violate the rules. And then these gray data points are all the materials listed in the ICSE, and then the colored data points are the ones where we, when we looked up band structures in the materials project, we gave them some credibility because there was no, like these compounds aren't magnetic, and their optimized structure was the same as the structure in the crystallographic CIF file. And so then we gave the points colors based on the electron counts, which should also tell us if hypervalent bonds are possible or not. And the first thing that we realized is, okay, 0 and 8 electrons, there shouldn't be any chemical bonds because should be happy, right? Counting to 8 was the rule. And all these green spots are up here, where the distance factor fails us. And so for 6 or 7 electrons, where some chemical bonding needs to be there, the points are down here. And then we gave them triangles if they have a beautiful, perfect band structure similar to zirconium silicon sulfides, and we gave them diamonds if they're somehow metallic. However, I would like to point out, I think I want to change the map in the future. These metallic ones, they still have the linear band crossings, just the Fermi level isn't perfect because they have an electron too much. And some, like these, they have some other bands interfering with it. But these crossings are there. So we can really quantifiably separate it just with the distance factor. So we can quantify this in an equation just based on lattice constant and Rykov coordinates of 1, we can have these bonds and these linear bands in these square net structures. And you might want to ask me why we don't just count electrons, because like electron counting gave a real result. And the answer is that this isn't as conclusive, because electron counting is sometimes when the electronegativity states in the elements are very similar to each other. It can just be can be very ambiguous, but this distance rule is not. Okay, so the next thing I was interested after looking at these square nets was the fact that the square nets really often want to distort. So they're at the borderline to some instability, which makes sense because the chemical hypervalent bond isn't really ideal. Ideal would be that they form some kind of zigzag chains and they form their two bonds they actually want to be chemically happy. So they're on a verge to a pious distortion, which also makes sense because we said, well, graphene doesn't do a pious distortion, but like based on the hydrogens, we should think it should. So something also interesting to look for is just that materials that are at the borderline to a pious distortion or charge density wave, like in 1D is a pious distortion and 2D is a charge density wave. And so we just wanted to look, once we start violating the hypervalent bond rules and we go away from the perfect electrons of 6 electrons per square net, what happens to the structure and if we start to induce distortions and if these distortions are of any interest to our property. And so we were looking at this material, gadolinium antimony telluride, which would have a perfect square net if we would have the 1-1-1 composition here. But if we start substituting some of the antimony with tellurium here, we go away from the perfect composition and we add electrons to the square net. And so this is a plot of the structure, and here at the 1-1-1 composition, slightly away from this, we have a perfect tetragonal structure with a square net, and we also would have linear bands and whatever comes with it. But if we go further away from it, we get an orthorhombic structure, so we start to get a distortion, and two of the structures we solve the crystal system, and we get just very complex arrangements of the square nets in here. So very long unit cells, which can be 4-fold or 5-fold enlarged. So complicated structural rearrangements. And we can look at these under the TEM. And okay, there's a lot of information on this slide, but basically this would be a TEM diffraction pattern of the perfect tetragonal case. And with low doping, there is no difference to be seen. But then at higher doping, we get all these extra diffraction spots here. And we can measure the distances here to get Q vectors of the charge density wave. And so we find that we have incommensurate charge densities for some charge density wave for some compositions and commensurate ones for others. And then because these materials contain gadolinium, they're also magnetic. So the structure distortion comes in hand with lots of complicated magnetic properties. So if we have the tetragonal material, we have only one magnetic transitions, but in the more complex incommensurate structures, we get up to 3 magnetic transitions. So we have now a system which started from topological band structure, goes on a complex distortion, and then exhibit complex magnetism. So if you look at, hey, okay, the slide doesn't work. Okay, now it works. So if you look at one of these a bit more closely, we can see how crazy the magnetism is. We really get like 1, 2, 3 transitions with a very field-dependent dip here, and this is the magnetic phase diagram of this with very complicated phases. So we're currently studying more details in physics of this phase. Okay. But so far I talked about materials that originate of this structure from square net, but there are all these other structures that have square nets in crystal structures, and that's basically one of the favorite things of solid-state chemists. Once we have some rule for one structure, the structural motif, we want to apply it to other structures which have these motifs. And you might know this structure type because strontium manganese bismuth 2 is also known to be a Dirac semimetals. And so these linear band crossings definitely also appear in these other square net structures. But I was interested in this structure because what I like about this is that for one, it contains rare earth, so we again have magnetism as a tuning parameter. On the other hand, it contains 2 square nets on top of each other. So these ones, the square match is always separated by something else, but here we have 2 on top of each other. And this gives us a possibility that we might be able to scotch tape the material to create a new 2D material. So I was wondering if like the typical properties that we find in materials with linear dispersed bands, like high mobilities, are also present in this material, just because we have square nets here as well, and if we then can scotch tape it to a thin material. So if you look at this materials in our tolerance factor plots, they all fall in this region here where the tolerance factor is working. However, we have 6.5 electrons rather than 6. Because of these materials are also known to undergo charge density waves. This is well documented in papers from Ian Fisher and Mercury Candidus already, but they start from the same from the same kind of motif, so I still wanted to see mobilities and all these properties have never been measured if we find anything. And so what we could, first of all, we checked if we actually can exfoliate these materials, and you can exfoliate them to thin flakes. They're also still magnetic. And what was surprising to us, and what we actually was hoping for, is when we put the bulk crystals in a magnetic field, we see beautiful quantum oscillations. And at the beginning, we reach mobilities of 30,000 centimeter squares by volt seconds in the bulk crystals. And now we're reaching up, depending which, if we fit the Hall conductivity or Hall resistivity, between 100,000 and 60,000 in the best crystals. So these bulk crystals are very highly mobile. They show magnetic, antiferromagnetic order at some point, and we know that we can make monolayers out of them. We haven't made any monolayer devices yet, but I think it's a very promising material to study in the future. And with this, I'm at the end. I hope I could show you that we can establish chemical rules based on chemical concepts for a certain structure motif of materials. And once we have these rules, we can use them to identify more materials of interest, and we can use them to find materials with magnetism at this other complexity, or look for distortions and what happens at the borderline to these materials. And we could also use them to find exfoliatable materials at short crystal properties. Thank you for your attention.
Oh, thank you, Leslie, for the interesting talk. Do we have plenty of time for questions?
So I have a question about the compound, whatever, tolerant 3.
Mm-hmm.
Sorry, I don't. So that's Galilean. Okay. Anyway, so you say it's antiferromagnet, like around 10 Kelvin. So 2 questions. First, is that a structure break inversion?
So there is it's a good question. So it does not at room temperature or above before the charge density wave comes in, but then the charge density wave makes it incommensurate. So it should, right? Because an incommensurate structure at lower temperature.
Sorry, the charge density wave, what's the transition temperature of charge density wave?
370 Kelvin.
So then for the spin, are they collinear or?
You don't know. So I couldn't do neutron diffraction on this because it has gadolinium, which eats all neutrons. We did the cerium analog and shipped it for neutron, but then the Oak Ridge time got cancelled last year, and now we're waiting for the next beam cycle. But also they are very different depending on the different rares. So I'm not sure if what we learned from the cerium will happen for the gadolinium. I'm trying to find collaborators who do X-ray studies with us for the magnetic structure.
These are very complex magnetic structures for sure.
So how does the CW transition temperature change as you bring it down?
Also a good question. So on the few devices we made, it changed, I think it went up in temperature.
It went up.
But we only have very few data points, so we need to make more.
Some of the heavier rarer has the second CW.
Yeah, exactly. Mm-hmm.
See how that
Yeah,
changes.
yeah, exactly. And that also changes with pressure.
Yeah.
I'm not sure if you said this or not, but are there a set of rules to know when you'll get charge density waves? Or could you imagine?
Yeah, we could probably think about really deriving them at their conclusive. So far I can tell you if definitely there are guidelines.
Yeah.
And I can definitely give you intuitive ideas of when a charge density wave should appear. It would be interesting to see if you can find something that always works.
What are the guidelines?
Well, basically, if you have something like a half-filled band, it's very likely you will get a charge density wave. Then if your chemical bonding doesn't fulfill the normal 8 electron count rules, and you have some other kind of bondings, it will always be at the borderline to the instability. But for example, this is not a full-on rule, because then zirconium silicon sulfide should have a charge density wave, but it hasn't, right? Or a graphene should
Possibly
have.
every Dirac material, which is a nice material, might.
Yeah.
Yeah.
What I'm saying is that Igor Malzahn wrote a very unknown paper. I mean, it's 240 citations, but it basically shows that the electronic mechanism that we think of nesting of charge density waves doesn't really happen. in
Right.
quantum materials.
I know this paper very
So
well,
you
and
can't
I
really-
completely agree with it, yeah.
Three-dimensional charge density waves are very complicated.
Yeah, exactly. But I think of them more as like structural distortions, similar to Fires distortion in more dimensions. And I know that there's a discussion of what comes first, the charge order or the structural order. I personally believe that it's always a structural effect.
There's a big difference between structural transitions and charge density waves, right? I mean, for example, all the AC conductivity, sliding motions, and so on, these are clearly itinerant phenomena that you will not get from a trivial structural distortion.
Okay, yeah, so I definitely have to do more reading, but this is just my general thing, but all the materials I studied that are charge density waves in the literature are structurally unstable.
Mhm.
So therefore, for me, this is kind of synonymous in the literature, but I just started digging into the charge density.
Yeah. Right, more questions for Leslie?
So related to this CDW discussion,
Mhm.
I guess naively I would think of CW as some nesting, and then really in this picture ignoring the wave functions or the orbital contents of the states in this K states. But now that you have a Dirac state in your system, I mean, if you take this into account, could that, I don't know, explain how this CW nesting doesn't really explain, the nesting picture doesn't really explain the Q vectors and all this.
Yeah, I have to do more reading of this thing because it's actually the question I would have asked you this question also. So I'm really, that's actually, I have been discussing with Niels and other people before. I really want to try to understand what is the difference because many of these materials for me chemically make sense that I have to distort, and therefore there's a structural distortion, and then it's called charge density wave for some reason, because often they have half filling and all these things that make them chemically unstable. And then this nesting picture doesn't really make sense for me. So I read Igor Marzin's paper that Andrew pointed out, and that really resonated with me because I never really got the nesting picture from a chemical.
The nesting picture is certainly wrong, but I think any attempt of having a very simple set of rules probably will be wrong.
Probably.
It's just hellishly complex. All right, any other questions for Liz? And maybe I do one as a break, because I had the pleasure of enjoying the talk before, so I'm really curious about the updates. So is there anything more in terms of hybridizing now these rare earth elements with the conduction band? So are we progressing towards making any of these square nets heavy? Or is this always separate magnetism from transfer?
Yeah, I don't have, since May I don't have updates. I just got students who started on this.
But do you have plans of progressing this direction?
We're going to study more of these rare earth materials and study them more systematically than just the one compound, but before. But so far, samples are only being kind of.
All right. But right now, if I remember correctly, none of them are heavy. Is that right?
None of them are heavy. Yeah.
In terms of heavy.
Yeah. Right. So the cerium antimony telluride, there's some debate. So I said it wasn't, but then some other people think it was too fast, and there's some aspects of heavy permeance with it. So that's why I want to study this more carefully, because I also realize you can make a doping study in this, similar as we did with the gadolinium. So that's something.
Given that heavy permeates are close to my heart, that would be topological. All right. Any other questions for Leslie? Well, if that's not the case, then let us thank Leslie again.